Hi, everyone. So this is just going to be a quick recap of last week's lecture on Friday. So I realized it wasn't recording when we were having our live lecture. So what I'm doing is just recording just a regular video lecture right now. So like I mentioned before, on the exam, I will not be including amines and amides. We'll cover those when we talk about amino acids. So I'm going to focus mostly on carboxylic acids and then esters, both naming and reactivity. So we'll start with carboxylic acids, right? So carboxylic acids, they are going to look almost like a combination of an alcohol and say like an aldehyde. So what we see is we still have that carbonyl group, but now we're going to treat this entire group of atoms, that carbonyl, oxygen, and carbon, and that hydroxyl group as now one functional group. The reason for that is like in this orientation, it will cause this H at the end to become acidic. And so that's what's giving the name carboxylic acid. And so below you can see there's three examples of a carboxylic acid. And in all cases, we find that carboxylic acid functional group. So in terms of naming, pretty much, again, we're following our regular IUPAC rules, where we're finding the longest carbon chain, and then we're finding what is our proprietary, or not proprietary, our priority functional group, the one that will change the ending, right? So if we look at something that's based off of one carbon, we would usually have the root methane if it was an alkane. Now when we have one carbon, but you have that carboxylic acid functional group, we remove the E off of methane and then we add the ending oic acid. So it becomes methanoic acid. Or another example of ethane, right? We can remove that E. So there's my 1, 2 carbons. And then I have my carboxylic acid functional group that becomes ethanoic acid. So again, we can follow our regular rules even when the structure gets a little bit more complicated. So again, we find there's my most important functional group based on this this molecule on the left-hand side, right? So we find the longest carbon chain. And if I was going to do that, it'd be 1, 2, 3. I could either say 4 or 4, either or, right? So we see we have excuse me, we have 4 carbons. So there's my butane. I have my carboxylic acid. So there's my butanoic acid. And then the last thing I need to take care of is that methyl functional group on the 3 carbon, becoming 3-methylbutanoic acid. I mentioned during lecture, other than benzene, the other cyclic derivative that I want you to know is going to be benzoic acid. It's because it's very common structure that you'll see a lot, especially in medicine. So it's good to be able to recognize benzoic acid. So that, just like benzene, right, it's almost has its own rule where we don't have like, a cyclohexane or something like that saying it's a cyclic 6-membered ring. Instead, the ending becomes, it's benzene, but now it's benzoic acid because the benzene has that this carboxylic acid at the 1 carbon. That dictates where 1 is, and then I need to keep my substituent groups at the lowest possible number. So I'm going to start numbering clockwise instead of counterclockwise. And I see I have 2 chlorines, one at the 2 and the other at the 3 position, becoming 2,3-dichlorobenzoic acid. So let's see if we can apply our rules to naming this structure, right? So it's in the skeletal structural form. So the first thing I need to figure out is what is my longest carbon chain? So I got 1, 2, possibly 3, but I can see I have 1, 2, 3, 4, 5 is actually my longest carbon chain. So 5, we know it's going to be pentan something. I notice my functional group is benzoic acid, so I know it's now pentanoic acid. And then I have that last substituent that I need to label where it is. Just like with aldehydes, the benzoic acid is always at the end or the terminal carbon, so it means it's an end carbon to the chain. So it always starts at 1, 2, 3, 4, and 5. I see I have the methyl group at the 2 position, so it becomes 2-methyl pentanoic acid. So again, a very structured approach to just naming. And now it's kind of a reverse problem. It's asking us, given the name, could I then reconstruct what the molecule looks like? And I can, right? We want, again, it's almost following the same procedure, but a little bit in reverse order. I see hexane is going to be my longest chain. So I have 1, 2, 3, 4, 5, 6. So there's my 6 carbons. Oic acid tells me that there is a carboxylic acid. So I could either write it like this, that's totally fine. Another option is to have your 6 carbons and then put the carboxylic acid on the other end. Doesn't really matter because you can do it in your mind. We could just flip that molecule around, right? Molecules exist in 3D space, so even though it looks different on a flat 2D surface, they're exactly the same molecule. So I'm going to stick with the way that I drew it on top, so I'll name that one. This always dictates where the number 1 carbon is, just like an aldehyde, because it's always at the end. So it becomes 1, 2, 3, 4, 5, and 6. And so then I see the last part of the name that I'm missing is 4-chloro. So then I go to my 4 position, and I add in a single chlorine. And let me get rid of my numbers, and then I'll be done. And there we go. There's fluorochlorohexanoic acid. So usually I've been having you just read the properties of certain functional groups without focusing during lecture, but something that I do want to focus on specifically are properties of carboxylic acids and what makes them acidic, right? That's going to be that's a really important function of carboxylic acids, is that it can affect the pH and then also participate in acid-base chemistry. So when we draw out explicitly, right, so I'm showing all the bonds of that carboxylic acid, we actually see there's 2 really electronegative atoms, the oxygens, and what they're doing is they're pulling a lot of electron density towards themselves, and it weakens this bond here between that oxygen and hydrogen, and that's what's going to make it acidic. Because remember, our definition of an acid is something that donates a proton. So the acidity of carboxylic acids, I can draw it like any other acid-base chemistry reaction, like when we had HCl and water, right? We said the acid will donate a proton, so it becomes chloride and hydronium. And that's a similar way we're seeing here. That proton, the acidic proton, can be donated to the water, forming hydronium, and it leaves behind the carboxylate anion. So a carboxylate looks exactly like a carboxylic acid, but it's missing that acidic hydrogen. That's the only difference. And remember, we're transferring something that has a positive charge, so the carboxylate ion is always negatively charged. So how do I name something that's going to be a derivative of a carboxylic acid? Well, it's pretty easy. What I need to do is remove the ic ending. So instead of being carboxylic acid, right? So methanoic acid, right? When it reacts with an acid-base reaction, right? We've seen this before. Something like HCl plus NaOH. When that reacts, it's going to form, well, if the H comes over, right? We're left with, oops, running out of space, but we're left with NaCl, which is a salt, and water. And it's exactly what we see when we take our acid and react it with the base. There's my salt and water. So how do I name that compound? It used to be methanoic acid. It's no longer carboxylic acid. Instead, it's a carboxylate salt. And so the way I change the name is I remove the ic acid and I replace it with 8. And since now it's also an ion, I need to name the cation. In this case, it's sodium. So it becomes sodium methanoate. It used to be methanoic acid reacted with sodium hydroxide to form sodium methanoate. And something similar, another reaction, right? There is our acid, there's our base. I create my salt, which is a carboxylate salt in water. And you may have heard this phrase, this compound before, potassium benzoate. It's usually used as a preservative. How is it made? Well, you take benzoic acid, react it with potassium hydroxide, and then it becomes a carboxylate salt. So there's my benzoate instead of benzoic acid. And then I mentioned the cation, which is potassium in this case. So to write out the reaction for propionic acid with sodium hydroxide, well, first I need to figure out what the structure of propionic acid is. Well, prop is going to tell me that there's 3 carbons. Oic acid tells me that I have a carboxylic acid. So there's my propionic acid. It's reacting with sodium hydroxide, which is a base. And so if I predict my products, right, what's going to happen is I will form water. So there's my H, there's my OH. So water is a product. And then what's left over is going to be my carboxylate. And that is going to have the counter anion or the counter cation of sodium. So if I draw that out, right, there is now my carboxylate. Oops, a little messy, right? That's propionate. And then it's going to be balance that charge with that sodium cation. So if I was going to name that, I have now made sodium propanoate. So all I did was take off the ic acid and put 8, so sodium propanoate. And there we go. So esters, I've decided to keep it pretty simple on this. Some of it is, well, we're going to need this when we start talking about DNA in chapter 17, right? So what is an ester? So the thing is, don't confuse it with an ether, right? An ether has, oops, that should be a C. Remember, it's a carbon, oxygen, carbon, with everything else kind of, what, I don't know, it could be just the carbon or it could be, the whole molecule. But it's that COC that is making it an ether. When we look at something that is an ester, however, there's my COC, just like an ether, but one of the carbons is connected to a carbonyl oxygen. And so it's that double bonded oxygen to carbon, OC, so the things that I have highlighted in yellow, that's the ester, right? And so esters are based off of carboxylic acids, and we'll talk about how to form esters as a chemical reaction. But if I look at how to name it, it's actually not that much different than naming carboxylate salts, right? So carboxylate salts, all we did, we took the base carboxylic acid name, say like ethanoic acid, right? If I took ethanoic acid and then I reacted that, just like on the last slide, with sodium hydroxide, right? What I'll form is, let's see if I can draw it small enough. Maybe I can't. I'm gonna have to, well, I'll do it down here. Right, what it becomes is a carboxylate salt in water, right? And the way we would name that would be sodium methanoate. So it's an ionic compound, that's why you have sodium, but now we have a covalent compound, but the naming doesn't change, right? We have our ethanoic acid, so I remove the ic acid and put 8 on the end, and instead of having a counter cation like the sodium, now we just have a carbon compound. It's a methyl group that's attached at that position. So just like when we had sodium ethanoate, now I have methyl ethanoate. The first one, the sodium methanoate, is in the carboxylic acid salt or carboxylate salt. The methyl ethanoate, because it's a covalent bond, it's actually an ester. So a subtle difference. So when naming esters, right, we follow a pretty standard way of naming them. It's a little bit different than naming for other compounds, right? But we're dividing the molecule into 2 halves. One, it will be the alkyl part. What it means by that is anything that's attached to the oxygen that's not near the carboxylic acid or not near the carbonyl carbon. So literally anything, it could be a giant molecule, it doesn't matter, a giant part of the molecule on this right-hand side. That would be considered the alkyl component. The other component is the carboxylic component. And how do I tell the difference? Well, because it starts to look a little bit like carboxylic acid. So what's in pink is the carboxylate, what's in blue is the alkyl part. So how is it formed? Well, it was formed from, and we'll talk about this maybe probably when we get to DNA, we'll actually do the actual reaction, but it's formed by reacting carboxylic acid with an alcohol. And so we have to get two different names, right? We have the ethanoic acid. It's going, so there's basically the derivative from ethanoic acid. Then we also to take into account the alkyl part. So it becomes methyl ethanoate. So just like I showed up on the other example. So if I was going to give this compound a name, right? So I got to determine where the alkyl part is and where the carboxylate part is. The carboxylate part is usually pretty easy because you find that carbonyl, oxygen, and carbon, and then it's anything connected to it. So what I can see is this looks like a derivative from methanoic acid. So I know it's going to be methanoic. Can't spell today. Let me fix that. Right, it looks like it comes from methanoic acid, so it'd be methanoate. Then I take a look at what's on the alkyl part. It's 1, 2, 3 carbons. 3 is going to be prop, so it becomes propyl methanoate. So it's kind of weird the way I wrote it. That should just be a space. It looks pretty big, but propyl methanoate would be the name of that compound. I know it's unusual the way it's written is that like the carboxylate side is on the left, and then the propyl part is on the right. I mean that like left and right, and then you kind of switch them in the name. Now the propyl becomes the right, and then the methanoate is the left. Don't let that confuse you. So there's my propyl ethanoate. Oh, did I write methanoate? Sorry, on the last slide, that was me. I think other people have made the similar mistakes too. Even I can make them, right? There's 2 carbons. I was thinking of only 1. So my mistake on that, but propyl ethanoate. All right, so I'm going to stop there because that covers everything that we covered during our lecture on Friday. Like I said, for the exam, I'm going to leave off amines and amides. It doesn't mean they're going away. It just means we're going to cover them later. So that should cover everything, and we're all set. So I will see you on Wednesday.